On the morning of June 5th, 2026, on Lake Taihu in eastern China, a small craft with two sets of wings accelerated across the water, lifted off, and then did something aircraft are not supposed to do. It stopped climbing. It leveled out roughly 30 to 50 centimeters above the surface, about the height of a kitchen counter, and held there at around 85 kilometers an hour, with the water blurring underneath it. It wasn't floating, it wasn't flying, not in the way you normally mean that word. It was riding on a cushion of its own compressed air, trapped between its wings and the lake. And if that sounds like a stunt, consider what it actually implies. Every ferry on Earth, including the one you might have taken across a bay or a river or a strait, spends almost all of its fuel doing exactly one thing: shoving water out of the way. This machine never touches the water at all. Stay with me, because by the end of this video you'll understand exactly why a boat physically cannot go fast without wasting most of its energy, why engineers have known the fix for over 60 years, and why that fix still isn't waiting at your local ferry terminal. Start with how big this actually is, because most people badly underestimate it. Ferries feel like a local thing, a tourist thing, a boat you take once on holiday. The numbers say something very different. A study commissioned by the trade association Interferry and carried out by Oxford Economics looked at the last full pre-pandemic year and found that in 2019, ferries carried 4.27 billion passengers worldwide. That is roughly the same order of magnitude as the entire commercial airline industry. They also moved 373 million vehicles across a global fleet of around 15,400 vessels, supporting an estimated 1.1 million jobs and about $60 billion of world GDP. For enormous numbers of people, a ferry isn't a novelty, it's the road. It's how you get to school, to hospital, to work, to the mainland, islands, deltas, archipelagos, river cities. Remove the ferry and the map stops functioning. And unlike almost every other form of mass transport, the ferry has no substitute. If a train line fails, there's a bus. If a road floods, there's a detour. If the boat doesn't sail, there is water, and that's the end of the conversation, which is why ferry timetables get treated like public utilities in the places that depend on them, and why the vessel's limitations quietly become the limitations of everybody living behind them. How far you can commute, how fresh the food arrives, how quickly someone reaches a hospital. All of it is capped by how fast a hull can be pushed through a liquid, and the machine doing all of that is, in its fundamentals, very old. A ferry is a hull. It sits in water, it displaces its own weight in water, and a propeller pushes it forward. Steam-powered versions of exactly that arrangement were running commercial crossings in the early 1800s. We have since gone from horses to hypersonic test aircraft, and the passenger ferry has changed in materials, safety systems, engines, and comfort, but almost never in principle. It is still a heavy shape being dragged through a liquid, which brings us to the part that stays invisible when you're standing on the deck watching the wake. Here's what's actually happening under you. Water is roughly 800 times denser than air. To move forward, a hull has to physically shove that water aside, and the water has to go somewhere, so it piles up. That's your bow wave. The trough behind it, the wake stretching out for hundreds of meters, the long rolling swell that slaps against the pier minutes after the boat has gone. All of that is energy, fuel your engine burned, converted into waves, and left behind in the sea. Naval architects call this wave-making resistance, and it has a nasty property. It doesn't rise gently with speed. As the hull speeds up, the wave it generates gets longer, and once that wave is about as long as the ship itself, the vessel is essentially sitting in a trough it dug for itself, trying to climb its own bow wave. Push harder and the drag climbs steeply. You can burn dramatically more fuel for a very small gain in speed. That is the wall. It's not an engineering oversight, and it's not something better engines fix. It's the physics of the boundary between water and air. It's why a typical passenger ferry cruises somewhere in the range of 20 to 40 kilometers an hour and not 200, and why the fast ones burn fuel at rates that make operators wince. The whole design is trapped in the worst possible place, half in a very dense fluid, half in a very thin one, paying full price for both. Engineers have been attacking this for a long time, and they've had partial wins. Catamarans use two slender hulls to make thinner waves. Wave-piercing bows cut through swell instead of climbing it. And the most elegant answer was the hydrofoil, which mounts underwater wings beneath the hull. Get moving fast enough, and those wings generate lift, the hull rises clear of the surface, and suddenly you've deleted most of the wave-making drag in one move. Hydrofoils genuinely work. They're in service around the world, but they run into a second wall, and it's a strange one. The wings are still underwater, and water doesn't behave like air. Push a foil fast enough, and the pressure on its upper surface drops so low that the water there begins to boil at ordinary temperature, forming tiny vapor cavities that collapse violently a moment later. That's cavitation. It wrecks lift, it makes noise, and over time it physically erodes metal. As New Atlas described it while covering this exact history, cavitation caps the practical speed of a hydrofoil at somewhere around 96 kilometers an hour, about 60 miles per hour. So you escape the drag of the hull only to hit the limits of the foil. The obvious next question almost writes itself. If the problem is the water, why stay in the water at all? Somebody asked that in the 1960s, and the answer became one of the strangest engineering programs of the Cold War. Pilots had long noticed something odd about flying very low. Close to the surface, an aircraft felt more stable, needed less throttle, and seemed almost unwilling to sink. What they were feeling has a name: ground effect. Here's the mechanism in plain terms. A wing generates lift by bending air downward, and the price of that is a pair of swirling vortices that spill off the wingtips and drag the aircraft backwards. That's induced drag, and on a normal aircraft, it's a significant tax. Now fly that same wing very close to a flat surface. Two things happen at once. The air being pushed down has nowhere to escape, so it compresses between the wing and the surface, forming a pressurized cushion that pushes back up, and the surface physically interferes with the tip vortices, so they can't fully form. Less induced drag, more lift for the same engine power. The wing gets more efficient purely by being close to something. A Soviet engineer named Rostislav Alexeyev, who had already built his reputation on hydrofoils and knew exactly where their ceiling was, decided to build vehicles that lived permanently inside that effect. The results were called ekranoplans, from the Russian for screen plane. The largest prototype, the KM, was around 92 meters long and weighed roughly 540 tons, and it crossed the Caspian Sea a few meters above the water at speeds reported near 500 kilometers an hour. When American analysts saw it in reconnaissance imagery in the 1960s, they reportedly nicknamed it the Caspian Sea Monster. It was faster than any ship and cheaper to run than an aircraft of comparable size. And then the program died, undone by technical compromises, internal politics, and eventually the collapse of the Soviet Union itself. For decades afterwards, the whole concept sat in the category of fascinating engineering footnotes, which is where China comes in, and it's worth being precise about the sequence because this isn't a single invention unveiled last month. It's a slow, deliberate buildup. The serious civilian groundwork was laid over a decade ago by the No. 702 Research Institute, also known as the China Ship Scientific Research Center, based in Wuxi. Their craft, Xiangzhou 1, completed testing off Sanya in Hainan and received airworthiness certification from the China Classification Society in 2014. The specifications are modest and very real: 12.7 meters long, 11 meters wide, 3.9 meters tall, a maximum takeoff weight of about 2.5 tons, 7 passenger seats, a cruise speed of roughly 140 to 160 kilometers an hour with a maximum near 210, and a water takeoff run of around 500 meters. Notice what that is. It is not a science project. It is a certified, civilian, 7-seat passenger craft doing island runs at motorway speeds without a runway and without a harbor. Then, this June, the concept got shrunk down to something a person could conceivably own. The craft on Lake Taihu was the WaveFly 5X from Navy, a Suzhou-based mobility company better known for electric scooters. The company calls it the world's first consumer-grade wing-in-ground effect vehicle. Here's how it does what it does. The structure uses a tandem dual-wing layout, meaning 2 wing surfaces front and rear rather than one large set, which matters enormously for stability. This is the hardest problem in ground effect flight. As the craft rises, the cushion weakens and lift falls. As it sinks, the cushion strengthens and lift rises. The center of lift also shifts fore and aft as height changes, which is what makes these vehicles want to pitch up or nose down. A tandem arrangement gives you 2 separated lift points to balance against each other, so the craft tends to self-correct rather than tumble. The body is aerospace-grade carbon fiber, which is not styling. Ground effect only pays off if the machine is extremely light for its lifting area because you are trying to fly on a fairly modest pressure difference. There's a second problem this design has to survive, and it happens before the craft ever gets airborne. To reach the cushion, the machine first has to accelerate while still sitting in the water, which means it must drag itself through the exact wave-making resistance it's trying to escape. Engineers call that region the hump, and it's the single most demanding moment in the whole flight. The engines have to be sized for a peak load that only lasts a few seconds, after which the craft needs a fraction of that power to cruise. It's why some designers, including the American teams working on larger versions, bolt on retractable hydrofoils purely to lift the hull far enough to break free before switching to air. Everything about a ground effect craft is a negotiation with those first few hundred meters. The published figures are deliberately unglamorous: a top speed of about 85 kilometers an hour, a maximum payload of about 140 kilograms, and a range of up to 80 kilometers. That's a 1 or 2 person craft for lakes, rivers, and calm coastal water. It is not a ferry. Nobody is claiming it is. What it demonstrates is that the control problem, the thing that killed this technology commercially for half a century, is now tractable enough to be handled at consumer scale and consumer cost. Cheap sensors, fast digital control, and modern composites have quietly done to ground effect what they did to multi-rotor drones, another idea that was theoretically sound for decades and practically useless until the electronics caught up. And this is where the story stops being about a leisure toy, because two very different things are happening in Chinese waters at the same time. In July 2025, open-source naval analyst H.I. Sutton identified a large ground effect craft on the Bohai Sea coast, writing it up for Naval News and nicknaming it the Bohai Sea Monster. Clearer photographs that surfaced in May 2026 corrected some early assumptions, showing 4 turboprop engines in paired nacelles above the wing and a joined tail arrangement, along with underwing hardpoints. It is a military program. Its designation, builder, and capabilities remain unconfirmed, and some analysts believe what's been photographed is a technology demonstrator rather than a finished design. But its existence tells you something. Reporting describes it as arguably the most ambitious ekranoplan actually built anywhere in decades. Meanwhile, China's state news agency, Xinhua, has cited estimates that the country's low-altitude economy, the broad category this sits inside, could reach 2 trillion yuan by 2030. When the toy end and the military end of a technology move at the same time, the middle usually follows. Quick question while we're here. If a craft like this ran your local crossing, half the journey time, no harbor needed, but flying a meter above the waves instead of floating on them, would you actually get on it? Or would you want to watch somebody else do it for a year first? Tell me in the comments. I'm curious where people land. And if you like technology explained honestly rather than hyped, subscribing genuinely helps this channel keep making these. Now the honest part, because this is where most videos on this subject quietly stop talking. The first barrier is waves. This is the big one. A ground effect craft flies inside a cushion measured in tens of centimeters to a few meters. If the swell is taller than your cruising height, the surface you're riding on comes up to meet you. Coverage of the Chinese military craft has noted that a true ekranoplan of that type is realistically limited to littoral water with waves under roughly 8 feet. A conventional ferry in that same sea state is uncomfortable. A ground effect craft in that sea state may simply not be able to operate. Ferry routes are contractual, scheduled public transport. An operator cannot tell a hospital-bound passenger that the crossing is canceled because the physics of the cushion has run out. The second is regulation, and it's genuinely awkward. These machines fall between 2 rulebooks. The International Maritime Organization has been working on this since at least 2002, when it issued interim guidelines for wing and ground craft, later replaced by a fuller set of guidelines in 2018. The framework sorts them into categories: craft certified to operate only within ground effect, craft with limited ability to climb out of it, and craft capable of sustained flight outside ground effect. That last category is subject to aviation rules as well, because the IMO and the International Civil Aviation Organization agreed that anything which can genuinely fly must answer to aviation authorities too. They also have to obey the same collision avoidance rules as ordinary shipping while closing on other vessels at aircraft-like speeds. Certifying a passenger service under that split regime is slow, expensive work. The IMO has even had to publish separate recommendations on the knowledge, skills, and training required for officers operating these craft, because the person at the controls is doing something that is neither seamanship nor conventional piloting. They're holding an aircraft 1 meter off a moving surface, in traffic, at speeds where a decision takes longer than the distance allows. The third is scale, and it's the least glamorous and most decisive. A large RoPax ferry carries hundreds or thousands of people, plus their cars and freight, and that mass is precisely what ground effect struggles with. Lift scales with wing area. Carry more, and the wings grow, the structure grows, the takeoff run over water grows, and the calm water requirement gets stricter. The 7 seats of Xiangzhou 1 and the 2 of the WaveFly 5X are not marketing conservatism. They're where the physics is comfortable right now. Then there's cost and noise. There is no announced production timeline or regulatory pathway for the WaveFly 5X, and reported price figures circulating around $100,000 are unofficial. Footage of the debut also suggests the craft is loud, which matters a great deal if the vision is thousands of these operating near shorelines and wildlife, and China is not alone here, which is worth saying plainly. In Singapore, ST Engineering's 10-seat Airfish 8 has been aiming at commercial operations pending regulatory approval, and in the United States, Regent has been sea trialing a 12-passenger electric craft with ferry and airline operators holding pre-orders. This is a field, not a single national breakthrough. So here's where it genuinely stands. The physics has been settled since the 1960s. The control problem, which is what actually killed it, is being solved right now, in public, at a scale small enough for one person to sit in. The certified 7-seat version has existed in Chinese service for over a decade. What hasn't been demonstrated is a large, all-weather, scheduled, certified passenger operation. Between here and there sit waves, rulebooks, and mass. And there's a quiet irony in all of this. Chinese state shipbuilder CSSC is among the largest builders of passenger ferries in the world by market share. The same industrial system that supplies the ferry is funding the research into the thing that skips over it. That's usually what a real transition looks like from the inside. Not a dramatic replacement, but an incumbent hedging against its own physics. So the ferry you take still works the old way today. It still burns most of its fuel making waves that nobody wants. And it will keep doing that for a long time yet, because it's reliable, it's certified, it carries your car, and it sails in weather that would ground everything described in this video. But the interesting question is no longer whether a vehicle can cross water without touching it. That was answered on the Caspian Sea 60 years ago, and it was answered again on a Chinese lake this June. The question now is whether anyone can make it big enough, safe enough in rough water, and boring enough in a regulatory sense to trust with a Tuesday morning commute, which leaves one thought worth sitting with. The reason your ferry is slow isn't a lack of engineering ambition, it's that we accepted the water as the road and then spent 2 centuries optimizing a vehicle for the most expensive possible surface to travel on. So how many other machines around you right now are built beautifully, efficiently, and expertly around a limitation that somebody, somewhere, has already quietly stopped accepting? Tell me which one you think is next in the comments, and subscribe if you want to see where this goes.